We're happy to start our Wednesday session with Raphael Bousso from Berkeley, who's going to tell us about quantum singularities. Please go ahead.
All right. Thank you so much. Thanks to the organizers for bringing us to this beautiful place and for letting me take part. So I'd like to talk about recent and so far unpublished work with my former student, Arvind Shahbazi-Moghadam. He's now a postdoc at Stanford. And the quick summary is that we show that regions that have too much entropy in them, in a sense I'll make precise, must have a singularity in their past or future. So it's sort of a new singularity theorem, if you believe the assumptions, of course, which is always the issue with these theorems. So singularities are not a super popular subject. In fact, many people go through in all of grad school without ever learning about any singularity theorems, and that's okay because I will review everything for you. So the definition of a singularity in general relativity is the presence of an incomplete time-like or null geodesic in an inextendable spacetime. The inextendable just means that your spacetime isn't singular because you did something stupid like remove a point from it. So it's as big as it can be, basically. It's not the proper subset of another spacetime. An incomplete time-like or null geodesic means that after finite proper time, like this guy here, or after finite affine time for a null geodesic, the geodesic just runs out of spacetime. There's nowhere to go, cannot be extended further. Physically, that's weird, right? It's what makes singularity so strange. You would expect that particles should have an infinite time to live after any particular time, or should have lived for an infinite time. So this is a past singularity here. I should say that on the left diagram, I'm showing a star that collapsed to form a black hole. The green thing is the star. And so then we have a future singularity inside the black hole. And on the right side, that would be the Penrose diagram for a spatially flat Friedman-Robertson-Walker universe. And there, of course, you have a singularity in the past called the Big Bang. So that's what a singularity is. This is not a perfect definition. There are things that we think are sort of singular, which are not captured by this. But it's pretty good, and it's the one for which you can prove things. So you can prove the presence of incomplete time-like or null geodesics from certain assumptions. And that's what Roger Penrose did in 1965, kind of introducing global methods to the subject and really revolutionizing the study of general relativity. And he did get a Nobel Prize for it last year. So his theorem, I want to review that. And in fact, I will spend a lot of time on the proof as well, because in the end, you just have to switch out a few ingredients to get from his theorem to the one that Arvind and I came up with. What we're going to consider, well, first of all, let me state the assumptions clearly. We're going to need the null energy condition to be true. That's the statement that light rays are focused by matter, not anti-focused, or roughly speaking, that to a light ray, the energy density looks positive. That's a hallmark of a classical sort of theorem in GR. It's the weakest of such assumptions that you can possibly hope to make. And we're going to assume that the space-time is globally hyperbolic, meaning that you can predict the past and future from some Cauchy surface, from some initial data. And now the theorem says, well, suppose you have an outer trapped surface. I'm slightly reformulating the theorem here for my purposes, but this is equivalent to what Penrose did. Suppose you have an outer trapped surface or an outer anti-trapped surface T. What do I mean by that? So what I mean is that the surface T itself is a two-dimensional surface, so like a sphere at an instant of time or something like that. It has to be compact. And outer trapped, the outer refers to the fact that there's one side of that surface which is spatially non-compact. So again, an example would be a sphere in Minkowski space, and then what we ordinarily call the outside of that would be non-compact. Right? You can, and the inside would not be; it would be compact. But the outside spatially would be non-compact. And if it is the case that light rays orthogonal to the sphere, either in the future or directed towards the past, have negative expansion, then it's called outer trapped. But that would not be true for a sphere in Minkowski space. The light rays that go off of it into the future or the past, of course, have the intuitive positive expansion. The sphere is getting bigger if you follow these light rays. And let me just make sure that this doesn't rub. Okay. So that's what is sort of special about these kind of surfaces. They behave in the counterintuitive way where the area gets smaller as you move away from them in the outside direction, in the sense of non-compact direction. So here are some examples. In the case of the black hole, a sphere right here, the blue dot inside the black hole near the big near the singularity has the property that not only its inside directed light rays towards the future are contracting, but also the outside directed ones, because you're in a black hole. And that's good because that's a non-compact direction. I'm showing that through the pink notation throughout the talk. That's the non-compact direction, or the one that in any case will be relevant for whichever theorem we're discussing. And so this sphere here is one for which Penrose's singularity theorem would diagnose that a singularity is about to happen in the future. Okay. And then conversely, in this expanding universe, the spheres here in this region on the left side near r equals 0 are normal. They're spheres like the ones we know and love in flat space-time. But the spheres, sufficiently large spheres, are dominated by the expansion of the universe, and in fact these outward directed, past directed light rays will be contracting towards the Big Bang, and so the theorem diagnoses the Big Bang. Okay, so I never stated the conclusion, but the conclusion is if all these things are true, then at least one orthogonal null geodesic is incomplete among all those geodesics whose expansion I'm discussing here. Okay. So how did Penrose prove this? By the way, I actually looked at this paper recently, and it's just infuriating. It's 2 pages, about 1 page of which is some blah blah blah, and then it's like puff up, finished. And it's amazingly powerful. So here's how he proves it. So he considers the light sheet L. I'm going to anticipate what this thing is by calling it a light sheet. That term didn't exist then. What is L? L is defined as the boundary. I'm going to specialize to the case where the singularity is in the future. So we're considering a future directed congruence, such as this one. Oh, where's my cursor? Oh, here it is. Such as this one inside the black hole. And so by L, I'm going to mean, the null hypersurface that's generated by these light rays coming out of T. More precisely, it's the boundary of the future of the interior, the brown region there. You look at its causal future, and the boundary of that is going to be L. So being the boundary of a set, L is going to be closed. The next step is to note that the surface T that we started from is by assumption compact, which means that if we know, again by assumption, that the expansion is negative, strictly negative everywhere on T, because it's compact, it can't approach 0 arbitrarily closely. So we can rescale the affine parameter at every point on T so as to make the expansion exactly -1. That's just for convenience. Now comes the assumption that we usually make in proofs like this. So for contradiction, we're going to assume that all null geodesics are in fact complete. In other words, there's no singularity. If that were true, then we could define a curly L, the red set, which we get by simply following all of these null geodesics for affine parameter distance 2. The 2 is important in a moment. I could have chosen any other number, of course, but 2 is kind of the one that will do the trick. And this red L, the curly L, is compact because it's the image of a continuous map from a compact set into the space-time. So let me show you an example here where there's no singularity. There's no singularity because I'm taking a sphere in Minkowski space, which actually has positive expansion in the non-compact direction. But just to show you what in that case the orange L and the red curly L will look like. The orange L, of course, will just be sort of an infinite light cone, well, minus the tip. So the light cone starts at T and just goes out forever. And the red L, the curly L, will be some finite piece of that. Notice that I've marked the exterior and interior, hopefully in consistent colors. All right, so that's not the case here. We have negative expansion. When you have negative expansion, you have the classical focusing theorem of general relativity, which is where we need the null energy condition, by the way. If you have negative expansion, you can prove fairly easily from the Richard-Roux equation that such a light ray will encounter a conjugate point at or before, 2 over the absolute value of the negative expansion that you're starting with. So in our case, that will be lambda equals 2. A classic example of that is the ingoing light rays for a sphere in Minkowski space. The conjugate point in that case is the tip of a sort of light cone that will be generated by those light rays. But it's really a local definition. So all you care about is that you have 2 neighboring geodesics that are moving towards each other, and you can prove that they will sort of intersect in a specific sense. So that's fact 1. It's a fairly trivial fact about GR. Another trivial fact about GR is that null geodesics leave the boundary of the future at or before. They could also leave earlier, but they leave no later than when they reach a conjugate point. Again, this light cone is a good example. If this was a light cone in Minkowski space, then they intersect each other here. They form sort of a new light cone, but the boundary of the future is the orange line. Okay, so what does this mean? It means that the orange L is a subset of the red curly L. The red curly L is compact and the orange L is closed. So by standard topology, that means that orange L is compact. So now this implies via another step that I won't discuss in detail, but which is hopefully clear from this diagram, that the spatial region, what I call the exterior of the surface T, is in fact compact, which contradicts our assumption that it should be non-compact. Right, so we wanted it to look like this. This was for Minkowski space where the expansion was positive, then the exterior indeed can be non-compact. But when the expansion is negative, the exterior has to be compact by the argument I just gave. All right, so now I'm going to state and prove essentially by substitution our new theorem. So our new theorem is the same as Penrose's, except that we replace the assumption that the exterior of the surface T be non-compact by a weaker assumption, namely that the entropy in what I'm going to call the exterior of T, though in many of the diagrams you're about to see, you might have been inclined to call it the interior. I'm just staying with this notation for continuity of the proof and of the statement of the theorem. So we're going to assume instead that the entropy of matter in the exterior of T is greater than the area of T divided by 4 times the Planck length squared. And so really what you want to do is look on both sides of T and see if that condition is satisfied. And if so, you just call that the exterior of T. Okay. Well, the price you pay in order to, so first of all, let me explain why that is a weaker assumption. In other words, I'm claiming that this is a stronger theorem than Penrose's. It encompasses all the cases that where Penrose can prove the existence of a singularity, but then a lot more. So the reason that it's a weaker assumption is that if you have a non-compact spatial side to a surface, you can always put an arbitrary amount of entropy there without changing the evolution of the metric. Right? So for example, think about the outside of a sphere in Minkowski space. That's non-compact, but maybe there's no matter there. And so it wouldn't, naively, it would not satisfy the assumptions of this theorem. Penrose's theorem would apply, but this one would not. There's no entropy, no matter. However, I can put some entropy there by putting extremely soft radiation out near infinity. I can put as many photons as I like. I can make their wavelength as long as I want. There's all that space. There's no problem putting as much entropy as I want with as little back reaction on the metric as I would like. And now I'm satisfying the conditions of our theorem. But since I haven't changed the metric, if the theorem predicts a singularity, which it does for that second case, the singularity must have been there in the first case as well. Okay, so that's how we get back to Penrose's theorem. But of course there's if you will, there's a price. I don't know if this is a terrible price, but what we have to assume is that the covariant entropy bound holds. The covariant entropy bound is the statement that the entropy passing through a light sheet of a surface is no greater than the area of the surface divided by 4 times the Planck length squared. So a light sheet, I'm going to discuss a quantum version of this bound in a moment, but this is sort of the classical version where you care about the classical expansion. And a light sheet is defined as a null hypersurface with everywhere non-positive expansion. So contracting light rays roughly, right? So again, as an example, a sphere in Minkowski space would possess 2 light sheets, namely the ingoing ones in the past and future direction, but no outgoing ones, because that's where the expansion is positive. Here, the reason that the covariant entropy bound will be easy to apply is that we haven't stopped assuming that the expansion at t is negative, just as we assumed that in Penrose's theorem. The null energy condition ensures that it stays negative because light rays can't anti-focus without first intersecting. And so automatically, the thing that we've been calling L really is a light sheet in the sense of the covariant entropy bound. So that's sort of the key new assumption that allowed us to prove this stronger theorem. So let's see how the proof works. I'm just really going to build on the previous proof. The previous proof already established that the domain of dependence of the light sheet is the same as the domain of dependence of what we call the exterior of T. In other words, they're unitarily equivalent to each other. They have the same data. They have to have the same entropy. I can evolve from one to the other. In this case, maybe the entropy consists of, the entropy of a bucket of water and the entropy of a box of gas. I add them up. That's the entropy that we care about. If that entropy is bigger than the area, I claim there's a singularity. Well, so if the entropy is in fact bigger than the area, then the covariant entropy bound is violated here, right? So because the domain of dependence is the same for L and for the exterior of T, it means that the entropy on L is the same as the entropy on the exterior of T. And by assumption, that's bigger than the area, and that contradicts the covariant entropy bound. So too much entropy means there has to be a singularity. And I'm going to go through a few examples to illustrate what this theorem can do that Penrose's theorem couldn't do. So the first example will be a collapsing star. What if we have a collapsing star that, unlike what I drew here on the right, actually is collapsing inside some universe that's not asymptotically flat? Maybe I don't know what the space-time looks like at great distances. How could it possibly matter if 10 billion light years from this star, the universe closes off or, keeps on being non-compact forever? I guess it can't be non-compact forever, but you know what I mean. Like it's somehow it seems like a random non-local faraway thing that should decide whether or not I can predict the singularity. It's a bit crazy. Well, in this example, we can choose T to be the surface of the star. So this is one of these sort of I don't know, popular book diagrams of a collapsing star, not a Penrose diagram where the singularity comes out here at the top like a little wick of a candle. And we choose the surface of the star at a late time. And we choose the exterior to actually be the interior of the star, because whatever the entropy is of this star, at a sufficiently late time, the area is going to become smaller than that. Right? And we can set things up so that we're not yet at Planck density or anything like that. We're completely in the semi-classical regime, have good control. In the Penrose diagram, you see what's really happening. If I start sending light rays inward into the future, they are going to get truncated by a singularity. They can't actually see all of the star. This is kind of the contradiction that's being exploited here. If these light rays didn't run into the singularity, then the light sheet would contain all of the entropy of the star. And if we choose this surface to be late enough and its area to be small enough, the entropy on the light sheet would be greater than the surface area. The singularity saves the covariant entropy bound. And that's sort of the logic that's being turned around here. We're using the covariant entropy bound to, well, we'll just assume it's true and use it to predict the singularity. So this could not have been, this surface T with the inward direction, without knowledge of what the spacetime looks like globally, you could not have applied Penrose's theorem to that. Another example are these things called bags of gold. Well, they have to be a bag of gold with a lot of entropy, so these things are sometimes called monster spacetimes. So what I have in mind is that you have a region of space. Let's suppose we don't know the answer yet, which is this spacetime diagram here. I just tell you that I have a region of space, let's say with time reflection symmetric initial conditions, so it's momentarily static, and it has the shape that I just drew here. So the two spheres are getting smaller, and then they're getting larger again, and there's a big bag, so to speak, behind a throat, and I can put a lot of entropy into that bag. This is easy to construct. For example, I can take a portion of a closed Friedman-Robertson-Walker universe filled with dust. I take more than half of it, right? And then by Birkhoff's theorem, I can just glue that to a portion of the Schwarzschild solution. And that's what I drew there on the right, the full spacetime diagram. So these are perfectly good initial conditions, and I can make that back. I can have it contain as much entropy as I like. I can dial independently what the size of the throat, in other words, the mass of the black hole is going to be. That depends on where I glue. Okay, so in that case, we can take T to be a sphere just outside the the horizon of the black hole that's going to form, which is why we're going to have a singularity. It's shown here. Okay, and this is, again, this is not what you would ordinarily call a trapped surface in any sort of Penrosian sense. It's actually a perfectly normal surface. These two light sheets L1 and L2 are both contracting. So if I put enough entropy here, our theorem would apply to either of them. And so we're predicting both a past and a future singularity, which indeed is present. When you actually solve the equations, you'll find that a black hole forms and the singularity is present here. And then finally, let's consider de Sitter space. So de Sitter space is this thing that looks sort of like a hyperboloid. It contracts exponentially and then expands exponentially. Has some sort of throat at a time symmetric slice that the spatial slices are three spheres, right? And the minimal size of the three spheres is set by the value of the positive cosmological constant. It's a vacuum solution, so just positive cosmological constant. The larger the cosmological constant, the smaller the throat. This is the Penrose diagram for de Sitter space. You see that two spheres at late time are going to be anti-trapped, and two spheres at early time are going to be trapped. This is a case where Penrose's theorem cannot apply because the spacetime is compact. There are no non-compact directions. This is why you can have a trapped surface here and not a singularity. And what we're going to do is we're going to go to some very late time, let's say, where this sphere is already exponentially large. That's supposed to be this gray slice. I really should have drawn it much closer to future infinity, but I want you to be able to see it. And so let me blow up that slice. It's really a three sphere. Let me blow it up into a two sphere. And now let me sprinkle some radiation on that enormously large two sphere. Just some radiation, thermal radiation at a very low temperature. So low that the radiation energy density is completely negligible compared to the energy density associated with the vacuum energy, the cosmological constant. And so I can neglect the back reaction up here. It's almost unnoticed. I can make it arbitrarily small. But if I do this at a late enough time, so holding fixed this very small radiation density, but now let me go to sufficiently late time, I can make it so that a hemisphere contains more radiation entropy than the area of the equator, just by scaling, right? The radiation entropy goes like the scale factor or the radius of the free sphere cubed, the area of the equator, the maximal two sphere on it goes like a squared. So for large enough a you know, the entropy wins. Once I do that, I can apply our theorem to the equator of that very late time slice. So here I've added this radiation. Now this could be, you know, billions of light years after we went through this throat here. Could be very, very late. And yet the theorem knows that if you run the equations backwards, now with this slightly modified initial data, sooner or later there has to be a singularity. What happens, of course, is that the energy density of this radiation gets exponentially amplified as you follow it back, and eventually it will start dominating over the cosmological constant. It will dominate over vacuum energy, and at that point you just have an ordinary closed radiation-dominated universe which has a Big Bang. Right. What's nice is that the theorem sort of diagnoses this from some fairly you know, remote location. All right. Any questions before I go on? Yeah.
Yeah, I was going to ask you about clarification of this black hole goal. So just to see if I got it. So what you're saying is that in fact this is a black hole space-time. So this has like a singularity behind the horizon, and there's a horizon that has the same entropy that's bigger than the one that's contained in that.
So the horizon, yeah, that's a very good question. Thank you. So first of all, the spirit here is that I'm going to give you only this one time slice as initial data, and we're going to pretend that I haven't yet solved the Einstein equations to figure out what happens. Right? Then the theorem tells you that there has to be a singularity, both in the past and in the future. So our natural guess would be that that's because a black hole forms. The theorem, of course, doesn't strictly speaking tell you anything about that. These singularity theorems are notorious for not telling you giving you any information about the specifics of the singularity, but that would be a natural thing to guess. Now, the black hole that actually does form is has the property that its Beckett-Stein-Hawking entropy is much less, or well, at least has to be somewhat less for this theorem to have applied in the first place, than the entropy behind its horizon. So this is why people were studying these monster spacetimes. It was sort of a way, I think, to recognize that whatever the Beckett-Stein-Hawking entropy is, it's not a bound on the entropy that you can put behind the horizon. And so, you know, you can find that confusing or not. Anyway, I think that was the original motivation for sort of bringing it up, saying like, hello, look, Beckett-Stein-Hawking entropy doesn't really constrain how much entropy I can put there. And that's just true. But yeah, this black hole, so its bifurcate horizon is this point here where the two blue lines cross, and that will have smaller Beckett-Stein-Hawking entropy than this green stuff has entropy.
And the other question was that you basically make this an asymptotically flat space. Again, I might have misunderstood. It sounded like your argument also applies in antidiscipline.
Yeah.
But it's a little bit more confusing now.
How so?
Because you have to be careful about the boundary condition.
Yeah, but this is so this will be like a two-sided ADS setup where you slice off part of the other side. So two-sided meaning take a Schwarzschild ADS black hole, right? And then on the far side of the bifurcate surface, you replace the asymptotic region with this bag. So instead of letting it go out again, it's really the same construction as a Minkowski space. and nothing comes out of the black hole to the right side. So you don't have to worry about what happens at the spatial boundary of ADS.
Okay, thanks.
Sorry, I also have a clarification question.
Yeah.
So I think it was the previous slide when you had the star collapsing. Can you go?
Oh yeah, 1 second. Here we go.
Yes, here. So here you can only predict that the singularity will form once you're sufficiently at late times.
Yeah.
So it takes a while to build up until you can predict that it's going to form a singularity. Is that correct?
That's right. So this is sort of I think a feature of all of these theorems, that they don't allow you to predict the singularity from any surface, right? But they allow you to predict the singularity. I mean, why was Penrose's theorem originally so significant? It's because it was very confusing to understand what happens when you go away from spherical symmetry, where you have control over the solutions. It looked like spherical symmetry, Schwarz's solution clearly has a singularity. But what if you just perturb this slightly? Couldn't all the particles miss each other and come back out or something? And maybe this is an artifact, it's a sort of solution of measure zero, and generically there won't be a singularity. And this was a huge big debate in the 60s, I guess, about which of these things is it. And there's good intuition, right, from other theories, like in Newtonian gravity. That's exactly what would happen. Things would just come back out. And so the point of this theorem is that it allows you to go to a place where you have complete control over the solution, and check a sort of qualitative thing, an inequality, which is either true or not, and then know that there's going to be a singularity. So, for example, the presence of a trapped surface, that fact is not going to change if I perturb my star a little bit. Right? As long as it was sort of not just on the threshold of not being trapped, but I go a little bit further in, and now I can add perturbations, and it's not going to change the fact that it's trapped. Similarly here, once I found a surface like this, if I change my solution a little bit, it's going to be still tell me that I will have a singularity. So that's sort of the spirit here, that there's a big sort of set of places where you have good control, and you know that the singularity is going to form. Yeah, great questions. Any other? Great, that works. Yeah, so I want to discuss a quantum generalization of this theorem, which has some advantages, but which also leads us to a puzzle, which I think is quite interesting. So there's a quantum version, or a quantum corrected version, if you will, of the covariant entropy bound, where you kind of put the area and the entropy all on one side and call it the generalized entropy. Okay. So let me first just give you the statement. The statement is that if the quantum expansion, I'll say in a moment what that is less than or equal to 0 away from some surface T, then the generalized entropy on the exterior of a later slice of the light sheet is going to be smaller than the generalized entropy on the exterior of the original surface. So first of all, what's the generalized entropy? Generalized entropy is the area of the surface in Planck units plus the von Neumann entropy of some side of the surface that we're going to call the exterior, whether it looks like the exterior or not. This quantity is better defined actually than each of the terms separately. The entropy, this is something I brushed under the carpet when discussing the covariant bound, but this entropy as a quantum field theory entropy, the von Neumann entropy, actually has a divergence, whose the leading divergence goes like area over cutoff squared. And this gravitational term can be thought of as a counter term. You can show, at least in some examples, that the RG flow keeps this sum fixed. So Newton's constant also suffers from an RG flow, but it goes in such a way that the sum is constant. And so we can make sense of this notion of a generalized entropy. This was first introduced by Bekenstein when he proposed the generalized second law, the claim that the area of a black hole plus the entropy on its exterior cannot decrease. Here, this T, of course, need not be on a black hole horizon. Yeah, and then the quantum expansion, well, it's the quantum corrected expansion. So the generalized entropy you can think of, Bekenstein thought of it as, well, we add another term to the ordinary entropy. But actually, this other term has a 1 over GH bar in it. So in some sense, it's a much more important term. And maybe a better way to think of the generalized entropy is as a quantum corrected area. Right? I start with the area, and then I add this term, which has an extra power of H bar in it. And similarly, I can quantum correct this geometric expansion, which was really just the rate of change of the area away from some surface that I start from, by asking about the rate of change of the generalized entropy instead. So I also include how the von Neumann entropy changes as I follow these light rays. So strictly speaking, you have to define this as a functional derivative. When you change the shape of some surface along this null congruence coming out of it, how does the generalized entropy change? Any questions about these definitions? Okay, so then the statement of the covariant entropy bound in this language is just that the light rays coming out of T, if they have negative quantum expansion, then we know that the exterior of T is going to have the exterior of sort of slices of this light sheet, such as this one T prime, is going to have less generalized entropy than the exterior that we started from. And why is it useful to have this quantum version? To give you an example, in some cases, you know, the sign of, I mean, usually for a sphere in this room, the quantum and the classical expansion are almost the same. The quantum correction to the classical expansion is completely negligible. But there are other situations where the two even have opposite sign. Okay, so here is an evaporating, here's a classical black hole, which is not yet evaporating. Okay, it's formed by the collapse of a star. Here is a surface T. So this is the left diagram. I don't know if you can see the cursor very well, but I'm looking at the left diagram. There's a surface, just a slice of the black hole horizon for simplicity, which by the by Hawking's area theorem, if you will, must have negative or zero expansion as you go towards the past. Right? That's the statement that the area of a black hole horizon grows towards the future. And so that means that the portion of the horizon that's in the past of T is a light sheet in the sense of the classical covariant entropy bound. Let me choose the exterior to actually be the interior, because it's useful right now. So in this case, the light sheet closes off, right? And you see that it contains the star that went in to make the black hole. So the covariant entropy bound tells us that the entropy of the star is less than the area of T, but the area of T is just basically the area of the black hole that formed at the end. Nothing else fell in. And so that's an example of the generalized second law holding true, right? The generalized second law says that the generalized entropy cannot decrease. And so since usually we think about the exterior, so in the exterior we would say the star has disappeared, but now we have this black hole of a certain area. And the black hole indeed more than makes up for the loss of the entropy of the star. That's what the covariant entropy bound guarantees us here. But as soon as we add quantum effects, the classical covariant entropy bound doesn't apply. When the black hole is evaporating, the area is decreasing towards the future. So this L that I drew here on the left diagram is no longer a light sheet according to the classical covariant entropy bound. Right. But the quantum expansion. So now I'm sort of turning the logic around. I'm using the fact that I know that the DSL holds. The quantum expansion is negative, and so I again get some consistency between the covariant entropy bound and the generalized second law. What this is saying in this case is that even though the black hole is shrinking in area, there's Hawking radiation produced on the outside, which more than compensates for that. You produce entropy on the outside. You also produce entropy on the inside, which here is called the exterior, because just as there are sort of Hawking particles peeling out of the vacuum on the outside, there are inside partners that they're entangled with and that purify them, that are peeled out of the vacuum on the other side of the horizon. And just for full generality, we don't need to insist that the region that we call exterior of T is connected. So it can have, let's say, two components. In this case, here T also has two components, which I'm calling TB and TR, and the regions that they enclose I call B and R. And we can apply the quantum covariant bound, for example, to deformations of the surface TB, so long as the quantum expansion is negative initially. So in that case, what we would care about is the quantum expansion of the system BR. You care about that, for the area, you would just care about what's happening locally near the surface TB. But for the entropy, you need to know everything, because B and R might have some entanglement. So we're going to need it to be true that the quantum expansion of the system BR is negative away from TB. And then if this light sheet L is complete, in other words, if it doesn't get cut off by a singularity, then the quantum covariant entropy bound tells you that the generalized entropy of BR, so the entropy of BR plus the area of the surfaces TB, TR, is greater than the entropy of just R. Okay, that's just the implication of the bound applied to this particular situation. And so we can again, and I won't go through the details, construct the singularity theorem out of that. Namely, if that inequality is violated, and assuming the quantum covariant entropy bound is true, then L cannot be complete. Some singularity must cut it off. Okay. The proof is actually a little more subtle because we can't use the classical focusing theorem. The null energy condition is no longer being assumed here. But there's a beautiful argument due to Wall, who proved a different kind of singularity theorem in 2011, that lets you show that null geodesics cannot stay on L for an infinite affine parameter distance if the quantum expansion is negative. So this leads to a puzzle. Namely, here is an apparent counterexample to the claim I just made. This is kind of the setup that you see in these kind of island calculations. You take R to be either an external system or just part of the future boundary of the space-time where a lot of Hawking radiation has accumulated. Let's say so much that we're after the page time. For after the page time, what does that mean? It means the area of the black hole is smaller than the entropy of the Hawking radiation that has already escaped. And a way of rephrasing that, so this S of R is the entropy of the Hawking radiation that's escaped. The area of the black hole is this thing, S gen of BR, because B and R essentially purify one another. R has the Hawking particles, B has all of their inside partners, so together they're in a pure state, and the only contribution to the generalized entropy is actually the area of TB. So the assumption of the theorem is satisfied here. We have negative quantum expansion going towards the past. We have a hyperentropic region in the sense that this inequality is satisfied. And yet in this diagram, you don't see a singularity. There should be a singularity in the past. And well, I'm out of time, so that's good because I also don't have an answer to this puzzle. I mean, obviously one possibility is that the covariant entropy bound is wrong, but I don't think so. I think that what this is telling us is something much more interesting. So I'll end with that. Thank you.
So in view of time, let's maybe just take one question and then postpone the rest to the meeting owl. Maybe we take one of the online questions, Maria. Oh, she was applauding. Okay, it was no question. Are there offline questions? All right, there aren't any. In any case, later on you can congregate here the owl. Then let's thank Raphael again.
Thank you.